Okay, hello everyone in a new video. In this one we are going to solve an exercise related to mechanics in the chapters of mechanical actions and equilibrium of a body. This exercise was a previous one in the brevet exams in 2015 second session third exercise. The title of this exercise is Gravitational Field Strength on the Moon. The aim of this exercise is to verify experimentally the relation between the values of the gravitational field strength Gm on the moon's surface and the gravitational field strength G on the Earth's surface. For this, we consider a spring R of stiffness K is equal to 50 newtons per meter, and a solid S of mass m, take G is equal to 10 newtons per kilogram. Then here, the moment we know the elongation of the spring or the compression, we can directly determine the tension in the spring. The moment we know the mass of the object, we can directly determine the weight. So here G represents the gravitational field strength on the surface, on the Earth's surface. Now first experiment. On the Earth's surface, we fix the extremity O of R to a support and we suspend the solid S to its free extremity A. So here they are talking about this document or this figure at equilibrium. So the solid S is at equilibrium, then now we can use the condition of equilibrium. The elongation of the spring R is delta L1 is equal to 12 centimeters. So this elongation corresponds for the gravitational field strength G is equal to 10 Newton per kilogram. So let me write here that delta L1 is equal to 12 centimeters. So this experiment being performed on the Earth's surface, knowing that centimeter is not the SI unit of length, in order to convert from centimeter to meter, we divide by 100, then 12 divided by 100. So the elongation delta L1 is given by 0.12 meters in the SI. Now S is submitted to two forces. Number one, give the name of each force. Now here, because the solid S, it has a mass, then it will be directly subjected to the first weight, to the first force, which is the weight. Then the first force is given by the weight W. And here, because we have a spring, that then it will be subjected to another force, which is given by the tension force, tension T. Now in number 2, we need to write the vector relation between these two forces, knowing that the solid S being at equilibrium. So let's say at equilibrium, then how do you apply this condition? Always on the left, we write the sum of different forces acting on the solid S, and they are given by the weight and the tension. So let's say W plus tension is equal to, because it is at equilibrium, then on the right hand side we'll write the zero vector. Here, because on the left we have vectors, then on the right the zero must also have a vector. Now moving T to the right hand side, so W vector is equal to minus T vector. So the first equation tells us that both forces act on the solid S in order for the solid S to be at equilibrium, whereas the second equation tells us that both forces have the same line of action. The minus sign is for the opposite direction and the equal is for also the same magnitude. Now in number 3, they are telling me to determine the magnitude of each force. So here we need to determine the magnitude of the weight vector W, which is given by W without a vector, and the magnitude of the tension T vector, which is given by T without a vector. So here, because we have the stiffness of the spring K and we have the elongation delta L, then by applying Hooke's law, we can directly determine the tension T in the spring. Then let's say apply Hooke's law. Hooke's law is given by that the tension T is equal to the stiffness of the spring, which is denoted by K, multiplied by the elongation, which is denoted by delta L1. Here, because delta L carries the index 1, so let's place here for the tension T the index T1. Now the value of k in the SI is given by 50. Notice that here no need to construct a triangle because this is the t is the quantity that we want to calculate, which is already on the left hand side, multiplied by the elongation delta L, which is given by 0.12. Now plugging this on the calculator, it will give me 6. Since both k and delta L are in the SI, so the value of Ti will be in the SI, which is in newtons. Then the value of T1 is equal to 6 newtons. Here in number 3 they are telling me to determine the magnitude of each force. So we already determined the magnitude of the tension T. Now it's left to determine the magnitude of the weight vector W. Here we don't have the mass, so we cannot calculate the magnitude W using W is equal to m times g. However, here in number 2 we have determined the condition of equilibrium, and this equation tells us that both forces have the same magnitude. Then let's write down here, because the W vector is equal to minus T1 vector, then in magnitude, let me write here, in magnitude, the magnitude of the weight is equal to the magnitude of the tension denoted by T1, but we already know that the magnitude of the tension T1 is given by 6 newtons, then the magnitude of the weight is given by also 6 newtons. And now in number 4 they are telling me to deduce that m is equal to 0.6 kilograms, and deduce means that we need to use the part just previously before. In part 3 we have determined the magnitude of the weight, which is given by 6, and we know that the value of g is given by 10. Then using that the weight is equal to mass times gravity, and constructing the triangle of this formula, here because we have multiplied and W will be at the top, m and g at the bottom, knowing that we are interested in calculating the value of m, denoted by capital M. The value of W is given by 6 and the value of g is given by 10. Plugging this fraction on the calculator, it will give me 0.6. Since both W and g are in the SI, so the value of m will be in the SI, which is kilograms. Then the value of m so here let me write that m is equal to 0.6 kilogram. Now we are in the second experiment. The same experiment is performed on the moon's surface at equilibrium. The elongation of r is delta L2 is equal to 2 centimeters. Let me make some space. Then now we are in the second experiment. Number 1, determine the new magnitude of each of the two forces acting on S, knowing that we have the elongation delta L2. L2 correspond for the second experiment being performed on the moon's surface. So the value of delta L2 is given by 2 centimeters. Knowing that centimeter is not the SI unit of length, in order to convert from centimeters to meter, we simply divide by 100. Then 2 divided by 100. Then the value of the elongation delta L2 is given by 0.02 meters. Now the tension can be determined directly from Hooke's law, because we have the elongation delta L2 and the stiffness K. So what we already have done in number 3. So we are repeating the same steps. Now let's say apply Hooke's law. Hooke's law is given by T is equal to K delta L. Here we are talking about the second experiment, which is corresponding for delta L2, and let's label T by the index 2. Now the value of the stiffness didn't change because this is a property related to the spring and it doesn't change from planet to planet. Now the value of K is given by 50 and the value of delta L2 is given by 0.02. Plugging this on the calculator, it will give me 1. Since everything in the SI, K and delta L, so the value of T2 will be in the SI, which is in newtons. Then T2 is equal to 1 in newtons. Now here in question number 1, they are telling me to determine the magnitude of each of the two forces. We already determined the magnitude of the tension T. It's left to determine the magnitude of the weight. The solid S being at equilibrium, so we can use the condition of equilibrium that we already determined in number 2, which is the vector relation, which is given by the W vector is equal to the minus T vector. So we are interested in the magnitude of this equation. So in magnitude, then the weight W is equal to the tension, which is denoted by T2, but we know that the value of T2 is given by 1 newtons. Then the new weight will be given by 1 newton. Now in number 2, they are telling me, knowing that the mass of S remains the same, deduce the value of Gm, and deduce means that we need to use the part just previously before, and the mass remained constant, which is given by 0.6 kilogram, and this can be done using W is equal to M multiplied by G. Now constructing the triangle of this formula, W will be at the top, M and G at the bottom. We are interested in calculating the value of G, which is denoted by Gm. What does the Gm represent? Gm represents the gravitational field strength on the moon, which is given by W divided by M. The value of W in this case is given by 1, and the value of M is given by 0.6. Plugging this fraction on the calculator, it will give me 1.67. Since everything in the SI, so the unit of G will be in the SI, which is the same of a G on Earth, Newton per kilogram. Then the value of a Gm is given by 1.67 Newton per kilogram. Now finally in number 3, we need to verify that Gm is equal to 1 over 6 multiplied by G. We need to verify this equality between the gravitational field strength on the moon and the gravitational field strength on the surface of the Earth. So here we have a question mark. Now the value of a Gm is given by 1.67, which is equal to 1 over 6. Now the value of G is given by 10. So on the left hand side 1.67, and on the right hand side 1 over 6 multiplied by 10. On the calculator it will give me 1.67. So indeed this is verified. So Gm is equal to 1 over 6 multiplied by G is verified. And by this we have finished solving this exercise. Hope it was beneficial for you guys out there watching it, and see you soon in another one.